Hi, everybody. We're here for homework 8. Um, First off, sorry if homework 8 is uninspiring. Um, as I've looked through this, it seems like we either set up some of these in class already, and the last two problems were on our activity, so don't feel like you have to do those twice. Um, yeah, I suppose you could be let down by the fact that there maybe isn't a whole lot of new content in this video, but maybe you were excited about the fact that there wasn't maybe a whole lot of new things to do on this homework. Um, Either way, what I like to do is try to do a good job of looking through these problems, understanding why they work the way they work, and yeah, we'll call it a day. We're not going to go into those last two problems because they're the same things that are on the activity. But, anyways, we are using a triple integral to find the volume of the solid F here in number 25. Okay, we don't have any picture. We have four equations. Um, hmm. What I would do with these is probably graph them initially, sketch graphs, and as I do that, try to think about what order of variables in integration will be the best for us. Okay, so first equation we have is x is equal to 1 minus y squared. Let's go ahead and draw an xy plane then. And since that is x is equal to 1 minus y squared, um, we would be intersecting the x-axis at x equals 1 when y equals 0. And this parabola will open to the left because we're subtracting y squared off. So yeah, no, x is equal to 1 minus y squared. Looks like that parabola. What else we got? X is equal to 0. Well, x equals 0 is just the y-axis. Okay, so we've got a region enclosed there. Let's see. Boom. Okay, so that's part of the integration that we're doing. We've got z equals 0 and z equals 1 minus x. Let's go ahead and make a zx plane. Yeah, if z is equal to 1 minus x, we would have 1 up here, slope of -1, and z equals 0 would be the bottom part here. So yeah, z equals 0 is the x-axis. And I guess we get x equals 0 again, this time for the z-axis. I mean, yeah. In actuality, everything that I've drawn in pink there is, well, that's the YZ plane. X equals 0 is the YZ plane. Okay, cool. So this is the region that we bounded there. Okay, and since we have x solved for in terms of y and z solved for in terms of x, I think x is going to make a good intermediate variable. And if we set up our first set of bounds with z first, then we'd be able to say that we can integrate from z equals 0 to z equals 1 minus x. And then after doing that, x in the middle sounds good. we'd be going from x equals 0 up to 1 minus y squared. And there we could be, looking at the first picture that we drew over here. And then when we integrate with respect to y at the end, it looks like that's going to be negative 1 to 1. But to figure that out for sure, we would set our equations equal to each other. So we've got x is equal to 1 minus y squared, x is equal to 0. Set those equal to each other and solve. We would get y squared is equal to 1. So y can be plus or minus 1. And good grief. That's why we need 1 and negative 1. Okay. So this looks like a good setup for that integral. And yeah, if we wanted to solve it, shouldn't be too bad. We would just have z evaluated at 1 minus x and 0. Cool, so we're just plugging in 1 minus x. Yep. Let's make some space here. Well, yeah, we might be able to scooch it up here and stay on the screen. Okay. Yeah, keep integrating. Nope, just kidding. Negative 1 to 1. When we integrate this, we'll have x minus 1/2 squared, or 1/2 x squared. Yep. And 0. There we go. We got the dy. Plugging in 1 minus y squared everywhere where we see x. So we'd have 1 minus y squared minus 1/2 1 minus y squared. And then we simplify this sum. All right. 1 minus y squared. Then we're going to have minus 1/2. In the middle of all that mess, we would have minus 2y. So, or minus 2y squared. So it would be plus y squared as something that's coming out of that. And then we would have plus y to the 4th. So minus y to the 4th over 4. Cool. dy. Okay, so this is actually, sorry, 1/2 minus 1/4 times y to the 4th dy. Okay, now we integrate and we're almost done. 1/2 y minus 1/20th y to the 5th, and we plug in 1 and negative 1. This is odd, so that's going to be a thing. Yeah, when we do this, it'll be ½ minus 1/20th minus negative ½ minus negative 1/20th. Goodness, sorry, running out of room. Scroll down just a little bit. Okay, so that'll be 1 minus 1/10. What did I do wrong? Right now, I've got 1 minus 1/10, but it should be 4/5 in the end, I think. Did I do something wrong up above? Yeah. Why did I put that over 4? I think I just got happy doing the y to the 4th thing, but that really should be y to the 4th over 2. Sorry. All right. This is what happens when I try to record videos and I don't have you guys to correct me in the moment. I make dumb mistakes and then it won't happen. Anyways, okay. We're going to change these to 10s. And then that is 1 minus 1/5, which is the 4/5 that we were hoping for. Cool. I think we're there. Yeah. Pretty solid. Okay. Next one. We've got a tetrahedron bound by that in the coordinate planes. The density is proportional to the square of the distance from the origin. And we're going to let our constant of proportionality be k. So yeah, we're going to calculate the mass integral, which is adding up a bunch of densities throughout the volume. So yeah, the biggest task, I think, would be setting up the bounds and then figuring out the integrand, but the integrand's not too bad. Since we're working with the tetrahedron and that is our top thing, and we've got the coordinate planes, yeah. That z equals 4 minus x minus 2y seems like a natural top surface. So as we set up this triple integral, 4 minus x minus 2y seems to be a good upper bound, and z equals 0 would be our lower bound for that coordinate plane. Yeah, and at the intersection of those two, 0 equals 4 minus x minus 2y would be the equation. Well, let's just solve for x. X is 4 minus 2y. And so that could be a good, good second equation where we go 0 to 4 minus 2y. And then the last one we can find where those intersect. So 0 is equal to 4 minus 2y. And y is equal to 2. Looks good there. 0 to 2. And yeah, those look like some good bounds. We just need to make sure that that matches with dz, dx, dy. In terms of the integrand, we've got the square of the distance, so x squared plus y squared plus z squared looks good for that. And then we would do, oops, just kidding, dz, dx, dy in the end. Oh, and I forgot the all-important proportionality constant k. Yeah, that one's not too bad. I think I just set this one up. Real quick, I will show you this if you're interested. This is maybe not too interesting, but this is what it would look like to solve that integral. Just a whole lot of polynomial stuff, so it's not super interesting. But in the end, if you went the extra mile and solved that one out, 96k over 5 would give you the mass of an object of that shape having density that is proportional to the square of the distance from the origin. Yeah, I don't know how many objects in real life have a density that's proportional to the square of the distance from the origin. One of the things that we will look at pretty soon is vector fields. And if you look at gravity as a vector field, being proportional to the square of the distance from an origin actually makes sense when you're thinking about gravity. So, maybe not so much in the physical space of density and stuff, but yeah, we're about to look at forces and vector fields, and yeah, that kind of a context actually makes sense there. Moving on to 14.5, we've got the cylindrical coordinate system to determine the mass of this solid. Cylindrical coordinates make a lot of sense because it looks like x squared plus y squared is showing up a bunch, and we're going to be able to utilize the fact that x squared plus y squared is equal to r squared. Yeah, so again, triple integral. Solid bounded by that in the plane z equals e. But we don't have a picture, and so maybe it would be good for us to think about which one of these is higher and which one of these is lower. Those two would intersect, z equals e and z equals e to the square root thing. Those would intersect when the exponent on e is equal to 1. And so it looks like, yeah, this is going to intersect when the radius is equal to 1. If x and y values were small enough that you were taking the square root of a number that was less than 1, then the z values would be lower. So I think that this is something that's opening up, and the flat plane is over top of it. So as we go ahead and make these bounds, since we're working in r dz dr d theta, since we're working in cylindrical coordinates, there's our volume differential. And yeah, for that first set of bounds, I think we put z is equal to e up on top. And then because x squared plus y squared is equal to r squared, this will be e is equal to the square root of r squared, or just e to the r. And so I think e to the r as a good lower bound is there. The density function here is the square root of x squared plus y squared, which is the square root of r squared as well, which is r. And so I think we put that inside of our integrand. And then, yeah, if we set z equals e equal to z equals e to the r, we've got at the intersection, intersect, e is equal to e to the r. Solving for that, r is equal to 1. We'll be looking at the radius going from 0 to 1. And since that's just the equation of a unit circle, we'll be going from 0 to 2 pi in terms of the angles. So I think that is a good way to set that one up. I don't know that I have the solution to the rest of that all worked out for you, but really the important part is setting this up and being able to set up the triple integral because, yeah, normally we will be able to have assistance when actually computing integrals at this stage in the game. Cool. 103. Set up a triple integral in spherical coordinates for the volume of the solid. I think we did this one in class 2. Sorry if this video is dragging on. This is the last one that we have. Because, yeah, the last one was just activity stuff. First octant portion of this sphere. So first octant portion means we want x to be greater than 0, y to be greater than 0, z to be greater than 0. Cool. For a triple integral in spherical coordinates, I guess the first thing that I'd want to do is translate this equation into spherical coordinates. The first move, I think, would be foiling out this z minus 3 squared into z squared minus 6z plus 9. That's equal to 9. I'm just kidding. 9. The x squared plus y squared plus z squared is equal to rho minus 6z will be minus 6 rho cosine phi. Sorry. Yeah, rho cosine phi is how you get the z value in spherical coordinates. And then that plus 9 at the end, I'm going to subtract 9 from both sides, and we'd just be left with is equal to 0. So we've translated this into spherical coordinates, and I think we could do even just one better by pulling out this common factor of rho and seeing that we've got rho is equal to 0, or wait a second. Wait a second. Oh, this is rho squared. Good grief. I'm like, where did the extra rho go? Yeah, that's rho squared. That's rho squared. Sorry, this is rho. But yeah, In spherical coordinates, x squared plus y squared plus z squared is equal to rho squared. Good grief. That one doesn't need a squared. This one doesn't need a squared. I think we've got our rows in a row. Now, yeah. So that second part, rho would be equal to 6 cosine phi. So those would be bounds on rho of cool. Let's go ahead and start making the triple integral. Rho equals 0 to rho equals 6 cosine phi on those bounds. We're just trying to find a volume of a solid, so our integrand will just be 1, but the volume differential is rho sine phi d rho d phi d theta. And yeah, to get the rest of this, we need to keep thinking about, okay, we're working with the first octant portion of the sphere. And so I think that that's going to bound us in terms of phi and theta. If we're working to the first octant, we'd go from the positive z-axis down to the xy plane. That's pi halves radians. So 0 to pi halves in the phi direction, and then in the theta direction, we'd be going from 0 to pi halves there just to get that first quadrant or octant, depending on what perspective you're taking. But yeah, I think that needs to be pi halves as well. So that was setting up that one, and solving for that would be kind of gross. And this video is already long. Thank you for, continuing to work in this class and continuing to learn. On Thursday, we will look at vector fields and hopefully some line integrals. And those won't be on our third test. But yeah, on Tuesday, we will review in the morning and have a test in the afternoon. I think that this third test won't be maybe as long as the other two. We've only gone through 6 sections worth of material for this test. And honestly, as evidenced by this homework, some of those sections don't really lend themselves well to great test questions. Some of them, I might just be having you set up some integrals. Some of them I'll have you solve all the way out. Yeah. And I'll try to make an announcement that gives you more details on what to expect on the test moving forward. And I'll try to have that to you before class on Thursday. All right. Hope you're having a good week. I'll talk to you later. If you want to meet via Zoom, that'd be fine. Office hours can be done via Zoom, and that would be cool. All right. Talk to you later.